Good afternoon, everybody. So I would like to welcome you all for one more webinar offered to you by Controlar. For the ones that don't know us, Controlar is a company with great expertise in test systems and automation systems for the industry, and we are specialized in the automotive industry. So this webinar, the topic for this webinar is differential signaling and automotive Ethernet, and the purpose of the webinar is to present to you the most recent innovations in this field. And to present this topic to you, I would like to present to you João Queiroz, that is an R&D project manager in Controlar, and he is specialized in industrial test systems. We would like to thank you all for being here, and I'm going to pass the word to João to start the presentation on this topic. Thank you very much.
Good afternoon, everybody. Thank you, Pedro, for this kind introduction. Let's start this webinar entitled Differential Signaling and Automotive Ethernet. Let's start with a summary so we can see what's expected on the road. I'll start by briefly explaining what differential signaling is and its main advantages and disadvantages when compared to single-ended signaling. Then I'll show some examples of where differential signaling is used in consumer electronics. Continuing to narrow the presentation, I'll show some usages of differential signaling in automotive communication buses. Narrowing even further, I'll briefly talk about the Automotive Ethernet. For the automotive industry, our core in Controlar, we develop automated test equipment for electronic components. As such, we have to deal with these communication interfaces on a daily basis, and we have had some problems with them in the past. I'll try to go through some of these problems. Finally, I'll show a very simple experiment that I made using a cable with unmatched lengths in order to verify its effects. Then in the end, I'll show some products that we have had that can help in maintaining the integrity of the differential pairs for the Automotive Ethernet and others. So what is differential signaling? Before getting into differential signaling, it's important to remember the relevance of wired connections in a wireless world. We all have wired connections in our homes or in our offices. Some are single-ended, some are differential, some are analog, others are digital, but all of them share one common aspect. They transmit data from one point to the other. Some even transmit data both ways at the same time, like Ethernet. Digital connections can be serial, where all the bits are sent one after the other on the same transmission path, or can be parallel, where several bits are transmitted at the same time in different lines, generally synchronized with the clock signal. The serial connections requires less transmission lines to establish the connection, and generally have high clock frequencies to send data at higher speeds, where parallel requires more wires but less frequency to send the same amount of data. Now that we already acknowledged the importance of wired connections, specifically the serial ones, where only one transmission line is required, let's see what is differential signaling. On the image on the left, we have the difference between single-ended signals and differential ones. Single-ended have one line that transmits the bits in a sequence and with a specific encoding. In this case, we have an encoding with only two voltage levels, V high for a binary 1 and V low for a binary 0. This could be a serial RS-232 port, for instance. RS-232 uses one wire for transmitting signals and another for receiving. Both lines are single-ended and reference to a single branch. On the other hand, the differential signal differs in the fact that it has two wires with complementary signals. On data plus, the signal with V high voltage translates into a binary 1, and V low translates into a binary 0. For data minus, the opposite occurs. On the figure in the right, we can see the advantage of this. When we have noise affecting the cables, it will affect both the data plus and data minus. This noise can then be subtracted on the receiver end, getting only the clean signal. By looking at this, we can see one of the challenges in manipulating differential signals. The data plus and data minus wires must be always together so that noise affects both in the same way. The main advantage of differential pairs is its immunity to noise. One big disadvantage, however, is the need of using two wires to transmit the same information. Differential signaling is used in many consumer electronic devices nowadays. A few examples are presented here with various different speeds and signal encodings. Many more could be here from different industry sectors. These are the more commonly available on consumer electronics, however. From our media centers with HDMI to our computers with EVI or USB, for instance, differential pairs are broadly used in many sectors of electronics. Now, let's focus on the automotive domain with some examples of communication buses that uses differential signaling. I tried to put these in a chronological order, but it's not easy to find the correct development and implementation dates. We can see from the speed graphic the various speeds that can be obtained. Starting with CAN, it's a low speed, up to 1 megabit per second, through bus topology, with multiple devices sharing the same single differential bus. FlexRay is very similar to CAN on the network topology aspects, but it can have two differential pairs and speeds up to 10 megabit per second. LVDS, more commonly used for video transmission, have had several iterations over the past years. One of the more recent ones introduced APX3, with speeds up to 12 gigabit per second over dual differential pairs. It supports only one master device and one slave device on each bus stretch. APX3 can transfer high-definition video and can even have a full duplex Ethernet connection over the same pairs. CAN-FD and the more recent CAN-XL are iterations of CAN, with added speed and message lengths. CAN-XL is still very recent, and its aim is filling the gap between CAN and 100 megabits per second Automotive Ethernet. Automotive Ethernet has two standards currently developed and in use, 100 base T1 and 1000 base T1, with speeds up to 100 megabit per second and 1000 megabit per second, respectively, on a single differential pair. These two standards are full duplex, meaning that data can be uploaded and downloaded at the same time at full speed. Like LVDS, it's a master-slave bus topology, but in this case, either side of the link can be master or slave with automatic or manual negotiation. A to B is a differential signal used for audio transmission inside a vehicle. It's also a full duplex differential pair that can transmit audio to slave devices on a daisy chain network and receive audio back from the slaves. It supports up to 32 different simultaneous audio channels or 16 stereo signals, adding to a maximum of 50 megabit per second. Focusing even further, let's talk about Automotive Ethernet. Currently, there are several standards already developed or under development. 100 base T1 and 1000 base T1 are fully released and in use in the market. 10 base T1S is still under development. It's a slower interface, just 10 megabit per second, but the idea is to be used like CAN on a multi-device network. 1000 base RH using plastic fiber is also under development for automotive usage. Other standards are being discussed, such as 2.5 gigabit per second and 10 gigabit per second. The main difference between Automotive Ethernet and Common Ethernet is the use of a single differential pair for the automotive. Both 100 base T1 and 1000 base T1 are encoded in PAM3 with 66 MHz and 750 MHz clocks respectively. These frequencies enables the possibility of using low-cost wires. Also, the spectral efficiency is higher for Automotive Ethernet, reducing the emitted EMI noise, removing the need for shielded wires. Both uplink and downlink data are transmitted at the same time in a full duplex communication on the same differential pair. Now, let's talk about the challenges when dealing with these signals in an automatic test equipment. When developing automated test equipment, many constraints can force us to make some commitments. One of the harder constraints to meet is the weight of the removable jig. In order to meet these requirements, the electronics must be placed outside of this testing jig. By doing this, we'll have an interface between the machine and the jig where all these differential lines must pass through. These interfaces aren't always compatible with high-speed signals, forcing us to use interfaces that sometimes are underrated, endangering the signal integrity by not meeting the correct differential impedance. Maintaining the pair together and length matching can also be a challenge if the signals must be galvanically isolated from the device under test using mechanical relays. Length matching is also very relevant on the PCBs that may be developed to any specific function. As these interfaces are getting faster, small length differences can disrupt severely the communication to a point where the connection cannot be established. Sources of high electromagnetic noise also may impact negatively the signal. For these cases, maintaining data plus and data minus as close as possible, preferably on the same cable, can help minimize the impact of noise on the signal. Although not required for many interfaces, using shielded cables may improve signal integrity in high electrical noise environments. Also, when developing PCBs, maintaining the correct differential impedance can also be a challenge. We, at Controlar, try to overcome these challenges as much as possible with custom-developed electronics and using, where possible, interfaces that meet at least the minimum criteria for the signal in question, and also by routing the cables through the best available places inside the machine. An example of this custom-developed electronics is our Bridge4NetG media converter. Next, I'll show a very simple experiment that I conducted with our more recent products. I'll use unmatched data plus and data minus lengths on an Automotive Ethernet connection to trigger communication errors. Using two Bridge4NetG media converters, I connected them together through the Automotive Ethernet interface with a cable that was cut and very badly reconnected. On the 100 base T, the common Ethernet side, one converter was connected to our internal network and the other to my computer. I then transferred a single large file from the network and verified that the average speed was far less than the expected 1000 megabit per second to a gigabit network. Simply looking at the speed returned by Windows, we can see that the speed decreased to half the nominal speed. This can have a big impact on the overall performance of a testing station, especially when large amounts of data must be transferred. Now, how can we help you? Through our line of products specifically designed to address some of the issues that we have been having these past few years and that I presented previously. Right now, if you have any questions about what I presented so far, please write them down on the question sections in Teams. First, our Bridge4Net 100 megabit media converter. It has a standard RJ45 for Ethernet connection and a low-cost automotive Molex connector for the Automotive Ethernet differential pair. It features a USB port for PHY configuration and debug. Information such as connectivity status or signal-to-noise ratio can be obtained from the PHYs. Also, master and slave configuration of the Automotive Ethernet is automatic upon power-up and can be manually configured using this USB interface. Custom firmwares can be developed if any specific configuration must be made statically. Bridge4NetG is a gigabit version of the previous one. All the debug and maintenance possibilities with a USB port are the same. Bridge4Net VPC was specifically developed to be attached to a VPC iDock interface. It features 4 media converters in different configurations. One media converter has both interfaces available inside the jig. There are 2 Ethernet interfaces available on the machine that are converted to 2 Automotive Ethernet inside the jig, and another one reversed with the Ethernet inside the jig and Automotive Ethernet on the machine. Also has 2 Ethernet pass-throughs interfaces and 3 USBs. It's compatible with our VPC interface that's composed of several other models currently available. The communication with the system is made via an API that's compatible with C# applications and also LiveView or test stands. This product helps in reducing the complexity of Automotive Ethernet connections, making these connections readily available on an interface inside the jig and using compliant high-speed VPC connectors. Our bus interface module 3.1 is a rack box with the capacity to include 15 PCB modules inside. These modules can be any that we already have developed, or custom versions can be developed to meet any specific requirement. With 15 Bridge4Net BIM modules, we can have 60 media converters in a 4U 19-inch rack box. This greatly reduces space and simplifies connection versus using 60 different converters. This product is relevant for multi-DUT systems, such as highly accelerated live test or highly accelerated stress screening systems. It can also be used in software flashing machines where an Automotive Ethernet connection is needed for each device. All 60 media converters can be used at the same time independently, or any of them can be dynamically switched off if needed. With this capability, several different configurations can be obtained using this product. We made a small animation video showing the applicability of these products, and I will show you right now.
I have to connect all these devices to my testing station through Automotive Ethernet, but how should I do it? Well, I suppose I have to buy several interfaces and stack them on my station. But now I have to connect all these interfaces with power and communication lines. It will be impossible to maintain such system. I wish there was an easier solution for this problem, like an equipment with more than one converter.
We have the solution for your problem. Our bus interface module 3.1 with Automotive Ethernet converters provides up to 60 converters in one 4U rack equipment. With a single supply and a single control interface, it's a much cleaner solution for systems with more than one DUT. The box is modular, with the possibility to add other modules for different functionalities. In the unlikely event of a malfunction, the modules are easily replaceable. For more information, send us an email to info@pt.controlar.com.
So this is just one rather funny video that we made to promote this product. Now, moving on, also on the differential pair subject, but now for the A to B, we are currently developing a generator and analyzer product that's able to work as master or slave in an A to B daisy chain bus. It will have the capability of generating audio or playing audio files and provide audio analyzing features such as FFT analysis, RMS measurements, among others. More information about this product is expected in the next few weeks. All datasheets and manuals and other information are available on our website, www.controlar.com. Thank you for your virtual presence. Hope to see you soon in another Controlar technical webinar. Let's continue safe and keep up the good work. And now to you, Pedro.
Thank you, João, for your presentation about this interesting topic. I hope the audience is enjoying this webinar so far. And just to remind you, you can write down your questions in the Q&A section here in the Teams platform. And I have, first of all, one question for João. That is, how, in your opinion, is going to be the future innovations in the field of the Automotive Ethernet?
Yeah, from what I've seen so far in some presentation made from many OEMs for the past years, I think there will be a paradigm shift, or it's already beginning, with the increase of electronic units inside the vehicle, to a new way of thinking the Ethernet, or thinking the connections inside the vehicle, with the domain controllers, which will be some type of model that will aggregate many sensors and many actuators on a single controller, and in domain controllers, so maybe several controllers inside the vehicle, but grouped or grouped by the function that they must provide, and they will all share information through some type of Ethernet, being the gigabit one or maybe the faster ones that are being developed specifically for the ADAS system, because it's a lot of information that has to go through. So I think that's the main innovation that's going to happen. It's already happening, but it will continue to happen for the next years.
Thanks for your explanation. Indeed, the automotive world is in a big change, and Controlar is going through that change together with our partners. So another question that has been made is about the prices of our solutions. So can you give some explanation about it? Thank you.
Yeah, for quotations, maybe it's better if you send us an email to info@pt.controller.com, and then we can analyze and provide the best quotation and the best technical explanations that we can do in order to help you. I think it's better than to be talking about prices right now.
Yeah, thanks. Indeed, it is the best option. Now, I think it's maybe also it is related to the price of the solution, about the flexibility of the solutions we have in here. So maybe it's also difficult to give a price when some of the solutions also are flexible, and it depends on the case they are applied.
Yeah, that's right.
So thank you all. If you have any more questions, I will give you a few moments for you to write them down here in the Teams platform. But in the time that I'm sure you are all writing down questions, I will just would like to remind you that the presentation that was made today and the recording of the webinar will be sent to all the attendees as soon as possible. And we are also going to send you a brief questionnaire to understand your opinion about this webinar, so we can improve the future events we offer to you. So since there is no more questions for our presenter, I would like to end this webinar, thanking the audience to be present during this time, thanking João to presenting us all all this knowledge he has, and we hope to see you soon in the next Controller event.
Thank you.